NENOMATICA, where mathematics meets YouTube excellence. Example: we will express the fourth root, sum of the roots of a quadratic, in terms of its coefficients. Let x sub 1 and x sub 2 be the roots of the quadratic x squared minus ax plus b equals 0, with a and b positive. Find the value of the fourth root of x sub 1 plus the fourth root of x sub 2. First, recall Vieta's formulas. The sum of the roots equals a, and the product of the roots equals b. We start by finding the sum of square roots. Let capital South equal the square root of x sub 1 plus the square root of x sub 2. Square both sides to relate it to x sub 1 plus x sub 2, and x sub 1 times x sub 2. Substitute a for the sum, and the square root of b for the square root of the product. Then solve for s by taking the principal square root, which is valid since a and b are positive. Now, let capital R be the sum of the fourth roots. We will raise r to the fourth power and use the binomial expansion. Group the middle terms cleverly so that square root expressions factor out. Finally, substitute our earlier results from Vieta and the value of s. Therefore, r equals the principal fourth root of that expression, which is positive. As a quick intuition check, imagine a equals 5 and b equals 4, so the roots are positive. Plugging these into the right-hand side gives a concrete number which matches the direct computation from the two roots. The algebraic identity is consistent. Summary: we used Vieta's relations for the sum and product of roots, found the sum of square roots. Example: we will maximize the sum of the squares of the roots of a quadratic. The equation is x squared minus, parenthesis t minus 2, close parenthesis, times x plus t squared minus 1 equals 0. We want the maximum of s, where s equals x1 squared plus x2 squared, and also the value of t where it occurs. Step 1. Express s using symmetric sums. Use the identity x1 squared plus x2 squared equals, parenthesis x1 plus x2, close parenthesis squared, minus 2 times x1 x2. Step 2. Apply Vieta's formulas to the quadratic. The sum of the roots equals t minus 2, and the product equals t squared minus 1. Step 3. Substitute these into s and simplify. We get s of t equals t minus 2 quantity squared minus 2 times t squared minus 1. Expanding gives minus t squared minus 4t plus 6. Step 4. Complete the square. To read the maximum directly, factor as minus, parenthesis t plus 2, quantity squared plus 10. Therefore, the parabola opens downward, and the maximum value is 10 at t equals negative 2. To make this fully intuitive, let's graph s of t. The vertex at t equals negative 2, s equals 10, is the peak of the downward opening parabola. Final answer: the maximum possible value of the sum of the squares of the roots is 10, and it occurs when t equals negative 2. In this lesson, we will minimize a symmetric expression in the roots of a quadratic. We are given the equation x squared plus px minus 1 over 2p squared equals 0. Let x1 and x2 be its roots. Our goal is to find the minimum value of a equals x1 to the fourth plus x2 to the fourth. First, recall Vieta's formulas. For a monic quadratic, the sum of the roots equals negative the coefficient of x, and the product of the roots equals the constant term. Here, that gives x1 plus x2 equals negative p, and x1 times x2 equals negative 1 over 2p squared. Next, rewrite the target in a symmetric way. x1 to the fourth plus x2 to the fourth equals the square of x1 squared plus x2 squared minus 2 times the square of the product x1 x2. Compute x1 squared plus x2 squared. From Vieta, it equals the square of the sum minus twice the product. Substituting the values, we get p squared plus 1 over p squared. Substitute these expressions into a. A equals the square of p squared plus 1 over p squared minus 2 times the square of negative 1 over 2p squared. On simplifying, we obtain a equals p to the fourth plus 2 plus 1 over 2p to the fourth. Now use the arithmetic geometric mean inequality on the positive terms p to the fourth and 1 over 2p to the fourth. Their sum is at least 2 times the square root of their product. Therefore, a is at least 2 times the square root of 1/2 plus 2, which equals 2 plus square root 2. Equality in AM. GM holds when the two positive terms are equal, so p to the fourth equals 1 over 2p to the fourth. That gives p to the eighth equals 1/2. Hence, any real p with absolute value equal to 2 to the negative 1/8 makes the minimum occur. So the minimum value of x1 to the fourth plus x2 to the fourth is 2 plus square root 2, achieved when the absolute value of p equals 2 to the negative 1/8. In this example, we will express S30 in terms of k using symmetric expressions in the roots of a quadratic. The quadratic is x squared minus 3x minus 1 equals 0, and we are told S10 equals k. Our goal is to find S30 in terms of k step by step. Let the roots of the quadratic be x sub 1 and x sub 2. By definition, S sub n equals x sub 1 to the n plus x sub 2 to the n. From Vieta's formulas, x sub 1 plus x sub 2 equals 3, and the product x sub 1 times x sub 2 equals negative 1. Step 1. Write S30 using the definition. S30 equals x sub 1 to the 30 plus x sub 2 to the 30. Step 2. Notice that 30 equals 3 times 10. Therefore, x to the 30 is the cube of x to the 10. We rewrite S30 as the sum of two cubes. Step 3. Apply the sum of cubes identity. A cubed plus b cubed equals the quantity a plus b cubed minus 3ab times a plus b. Here is x sub 1 to the 10, and b is x sub 2 to the 10. Step 4. We substitute S10 equals k. Replace the sum x sub 1 to the 10 plus x sub 2 to the 10 with k. Step 5. Evaluate the product factor using Vieta's product. Because x sub 1 times x sub 2 equals negative 1, the product to the 10th power is negative 1 to the 10th, which equals 1. Finally, simplify the expression. S30 equals k cubed minus 3k. In this lesson, we will derive a beautiful recurrence for symmetric expressions in the roots of a quadratic. Our goal is to follow a clear, algorithmic sequence of steps. We begin with an example label, followed by the problem statement, just as a clean slide introduction. Step 1. Consider the quadratic equation, ax squared plus bx plus c equals 0, with roots x sub 1 and x sub 2. Define capital S sub n to be x sub 1 to the n plus x sub 2 to the n. We will show that the sequence S sub n satisfies the recurrence a S sub n plus bs sub n minus 1 plus cs sub n minus 2 equals 0. Step 2. Define the early terms in the sequence explicitly and multiply the quadratic by x to the power n minus 2. Then multiply both sides of the equation by x to the n minus 2. Step 3. Distribute and use exponent laws. The left side distribute and use exponent laws. The left side becomes ax to the n plus bx to the n minus 1 plus cx to the n minus 2 equals 0. Step 4. Because x sub 1 and x sub 2 are roots of the original quadratic, the polynomial equals 0 at each root. Replacing x by x sub 1 and x sub 2 in the expanded equation yields a small system, which we then add together. Step 5. Recognize each symmetric pair as S terms. We obtain a S sub n plus bs sub n minus 1 plus cs sub n minus 2 equals 0. If it is not 0, divide everything by a to get S sub n plus b over a times S sub n minus 1 plus c over a times S sub n minus 2 equals 0. N minus 1 plus c over a times S sub n minus 2 equals 0. Step 6. Rearrange to the standard recurrence form by setting q equal negative b over a, q equal negative b over a, and p equal negative c over a. Then S sub n equals q times S sub n minus 1 minus p times S sub n minus 2. In this example, we will compute S4, which is x1 to the power 4 plus x2 to the power 4, for the quadratic equation x squared minus 5x plus 2 equals 0, using symmetric sums and a clean recurrence. We will also identify the sum and product of the roots using Vieta's formulas. Step 1. From Vieta's formulas for a monic quadratic x squared minus qx plus p equals 0, we have the sum of roots q equals x1 plus x2, and the product of roots p equals x1 times x2. For our equation, the sum q equals 5, and the product p equals 2. Step 2. The power sums Sn defined as x1 to the n plus x2 to the n, follow a simple recurrence derived from the characteristic equation. Sn equals q times Sn minus 1 minus p times Sn minus 2. We will use it to reach S4. Also remember that S0 equals 2 and S1 equals q. Step 3. Using the well-known identity S2 equals S1 squared minus 2p, we can compute it numerically. With q equal 5 and p equal 2, S2 equals 25 minus 4, which is 21. Step 4. Next we compute S3. The identity is S3 equals S1 cubed minus 3ps1. Plugging the values gives S3 equals 125 minus 30 equals 95. Step 5. Now use the recurrence to reach S4. S4 equals q times S3 minus p times S2. That is 5 times 95 minus 2 times 21, which equals 475 minus 42, giving 433. Therefore, the final value is S4 equals 433. Quick recap. Using Vieta, we found q equals 5 and p equals 2. Then S0 equals 2 and S1 equals 5. We computed S2 equals 21 and S3 equals 95. Finally, the recurrence S4 equals QS3 minus PS2 gave 433. Try practicing with another quadratic, for example x squared minus 6x plus 5 equals 0, and compute S4 yourself. In this example, we solve a symmetric expression built from the roots of a quadratic. We'll work step by step to derive a simple recurrence, and then evaluate the requested fraction. Here is the problem statement on screen. Step 1. Let alpha and beta be the roots of the quadratic x squared minus x minus 4 equals 0. We define p sub n as alpha to the n minus beta to the n. Because alpha and beta are roots, each satisfies the quadratic equation. Step 2. Multiply the first equality by alpha to the power n minus 2 and the second equality by beta to the power n minus 2. Expanding gives alpha to the n minus alpha to the n minus 1 minus 4 alpha to the n minus 2 equals 0, and beta to the n minus beta to the n minus 1 minus 4 beta to the n minus 2 equals 0. Step 3. Subtract the second expanded equation from the first. The differences group naturally into p sub n minus 1, and p sub n minus 2. That yields the recurrence p sub n minus p sub n minus 1 equals 4 times p sub n minus 2. Step 4. Apply the recurrence 3 times to the numerator. P sub 15 minus p sub 14 equals 4p sub 13. P sub 14 minus p sub 13 equals 4p sub 12. P sub 13 minus p sub 12 equals 4p sub 11. Multiply these three results and divide by p sub 13, p sub 12, and p sub 11. All three factors cancel, leaving 4 cubed. Therefore, the value of the expression is 64. Our key idea was to convert a symmetric difference of powers into a simple linear recurrence by using the fact that each root satisfies the quadratic equation. Example: we are given the quadratic x squared minus 6x plus 1 equals 0. Let x sub 1 and x sub 2 be its roots. We will prove, step by step, that s sub n equals x sub 1 to the n plus x sub 2 to the n is always an integer, and is never divisible by 5. From Vieta's formulas, we immediately get the sum x sub 1 plus x sub 2 equals 6, and the product x sub 1 times x sub 2 equals 1. These two facts will drive everything we do next. Now we derive a simple recurrence for s sub n. Start from the binomial identity x sub 1 to the n plus x sub 2 to the n equals x sub 1 plus x sub 2 times x sub 1 to the n minus 1 plus x sub 2 to the n minus 1 minus x sub 1 x sub 2 times x sub 1 to the n minus 2 plus x sub 2 to the n minus 2. Substituting the Vieta values, we obtain s sub n equals 6s sub n minus 1 minus s sub n minus 2. Let us compute the first few terms. S sub 0 equals x sub 1 to the 0 plus x sub 2 to the 0, which is 2. S sub 1 equals x sub 1 plus x sub 2, which is 6. Using the recurrence, s sub 2 equals 6 times s sub 1 minus s sub 0, which is 34. because the recurrence has integer coefficients, and we have integer initial values. Every subsequent s sub n is an integer. Next, we study divisibility by 5 by working modulo 5. Since 6 is congruent to 1 modulo 5, our recurrence becomes s sub n congruent to s sub n minus 1 minus s sub n minus 2 modulo 5. Starting with s sub 0 congruent to 2 and s sub 1 congruent to 1, we can quickly generate several residues. Notice that none of them are 0. Reading across the bottom row, we get the sequence 2, 1, 4, 3, 4, 1, 2, and so on. It repeats and never hits 0. Therefore, no s sub n is divisible by 5. Final result. For the quadratic x squared minus 6x plus 1 equals 0, the symmetric sum s sub n equals x sub 1 to the n plus x sub 2 to the n is an integer for all n, and it is never divisible by 5. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.